Hi everyone, welcome to lecture 26 on relative frequency. The objectives for this video are the following. After watching, everyone should be able to, number one, calculate relative frequencies from a finite number of trials. Number two, explain how relative frequency informs us about degrees of belief about chances. And number three, explain why the larger the number of trials we observe, the more compelling a report of relative frequency becomes. So, recall from lecture 25 part 1 that we're looking at the following three kinds of probability: rational degrees of belief, relative frequency, and chance. We've covered degrees of belief in some detail, and in this lecture we're looking at the second one, relative frequency. Now this is perhaps the most straightforward one to understand, so let's have a look at what we mean when we talk in terms of relative frequency. Suppose I flip a coin 10 times and it comes up heads 6 of those times. Then very simply we say that the observed relative frequency of heads is 6 out of 10, or 0.6, because we've observed 6 heads out of 10 trials or flips of the coin. Now observed relative frequencies work the same way for any finite number of trials, so if you flip a coin 20 times and it comes up heads 14 of those times, then the observed relative frequency of heads is 14 out of 20, or 0.7. So to test that, here is a quick question. Now, relative frequencies, as the book says, obey the laws of the probability calculus that we've developed, just like the other kinds of probability do as well. So they're always numbers in the interval 0, 1. The relative frequency of a tautology is always 1, and the relative frequency of a contradiction is always 0. And the relative frequency of two mutually exclusive outcomes is the sum of their individual relative frequencies. So why do we care about talking in terms of relative frequencies? Well, statements of observed relative frequencies constitute an especially important kind of evidence that inform our degrees of belief about chances. Now, we haven't looked at chances yet, or what they are, but as we'll see in the next video, that's quite a difficult question to answer. And if we're thinking about coin tosses, we'll proceed on the vague intuition that we think there is some true chance that a coin has of landing on heads, perhaps determined by its physical composition, for example. So how do relative frequencies serve as evidence for telling us about chances? Well, let's look at a simple coin example. Suppose we're uncertain whether a coin is biased, and we think there are three possibilities. Either the chance the coin comes up heads is 0.25, the chance it comes up heads is 0.5, or the chance it comes up heads is 0.75. Now let's suppose we flip it 10 times and we get some outcome. And let's suppose we want to know the probability that the coin has a 0.25 chance of coming up heads given the outcome of our coin flips. Remember that because we are uncertain about the chance of heads associated with the coin, this probability is our degree of belief that the coin has a 0.25 chance of coming up heads given the outcome of our coin flips. So we're reasoning under uncertainty here. And whenever I say probability in what follows, they are our degrees of belief that we're talking about here. So using Bayes' theorem, we see that the probability that the chance the coin comes up heads is 0.25 given the outcome is equal to the probability of the outcome given the coin has a 0.25 chance of coming up heads times the probability that the coin has a 0.25 chance of coming up heads, all divided by this thing, the probability of the outcome given the coin has a 0.25 chance of coming up heads times the probability that the coin has a 0.25 chance of coming up heads, plus the probability of the outcome given the coin has a 0.5 chance of coming up heads, times the probability that the coin has a 0.5 chance of coming up heads, plus the probability of the outcome given the coin has a 0.75 chance of coming up heads, times the probability that the coin has a 0.75 chance of coming up heads. And a similar thing holds for the probability that the coin has a chance of 0.5 of coming up heads given the outcome, and for the probability that the coin has a chance of 0.75 of coming up heads given the outcome. The point here is that, as we saw in lecture 23, the evidence here is the outcome on the left-hand side, but all of the information about that outcome is contained in a report about the observed relative frequency of, in this example, heads in that outcome. For example, if the outcome is heads for the first 5 flips and tails for the next 5 flips, then what we've written above reads like this. So all I've done here is written the actual outcome in instead of the word outcome, and let's call this equation 1. But let's say we flip the coin again 10 times and it comes up heads, tails, heads, tails, heads, tails, heads, tails, heads, tails. Then if we write that in for the outcome, Bayes' theorem tells us this. So let's call this equation 2. Again, all I've done here is replace the word outcome with the outcome itself. And now we look at the right-hand sides of equations 1 and 2. The point is that the probability of outcome heads, 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 tails, 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 given that the coin has a 0.25 chance of coming up heads, is equal to the probability of outcome heads, tails, heads, tails, heads, tails, heads, tails, heads, tails, given that the coin has a 0.25 chance of coming up heads. This is because the trials or the coin flips are independent, conditional on the chance hypothesis. So the probability of the outcome, given the chance hypothesis, is just equal to the probability of the outcome. That, remember, follows from the definition of independence. And this holds no matter what the chance hypothesis is. So similarly, the probability of outcome heads, 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 tails, 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 given that the coin has a 0.5 chance of coming up heads, is equal to the probability of outcome heads, tails, heads, tails, heads, tails, heads, tails, heads, tails, given that the coin has a 0.5 chance of coming up heads, and the probability of outcome heads, 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 tails, 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 given that the coin has a 0.75 chance of coming up heads, is equal to the probability of outcome heads, tails, heads, tails, heads, tails, heads, tails, heads, tails, given that the coin has a 0.75 chance of coming up heads. So the right-hand sides, this is the upshot of equations 1 and 2 are equal. The idea is that it doesn't matter what order your 5 heads come up in when you flip your coin 10 times. All you need is the fact that there are 5 heads, whatever flips they come up on. And how do we express the fact that 10 coin flips turn up 5 heads regardless of the order? That is just to say that the relative frequency of heads on those 10 coin flips is 1/2. So all you need to calculate your degrees of belief, for example, like we've used here, that the coin has a 0.25 chance of coming up heads given some outcome, is the relative frequency of heads in that outcome. So this is how relative frequency serves as evidence about our degrees of belief about chances. And this addresses our second objective from back at the beginning. So let's look at our third objective, which told us that we have to be able to explain why the larger the number of trials we observe, the more compelling a report of relative frequency becomes. This is explained in essence by a theorem. We're going to state a simplified version of it here, and we won't prove it since that takes us a little beyond the scope of the course. The version of the theorem that we'll use says this, and it's called the weak law of large numbers. Now this one is formulated in terms of coin flips, since that's the example that we've been looking at. It says, fix any epsilon greater than 0, then the limit as n goes to infinity of your degree of belief that the observed relative frequency of heads minus the chance of heads is less than epsilon equals 1. Now we can unpack this a little bit. Because this works for any epsilon bigger than 0, the idea is that we consider tiny values of epsilon, so stuff very close to 0. So we can take epsilon as close to 0 as we like. Then what does this taking the limit as n goes to infinity mean? It means we flip more and more and more coins each time. N, remember, is the number of tosses. So it tells us that as we flip more and more and more coins, our degree of belief that our observed relative frequency of heads minus the chance of heads is below epsilon, so that's very, very small now, so those things are very, very close to being equal. Our degree of belief that those things are very, very close to being equal is equal to 1. And that is to say, as we flip more and more and more coins, we become more and more certain, that's the probability 1 part, that our observed relative frequency of heads equals the chance of heads. So the more coins we flip, the better informed we are about the chance of the coin coming up heads on the basis of our observed relative frequencies. And that's why the larger the number of trials we observe, so the more coins you flip, the more compelling a report of relative frequency becomes. It's a compelling report, of course, of the chance that in this example that the coin comes up heads. So what have we seen? Even when we're uncertain about chances, relative frequencies are evidence that informs us about chances. And the more trials we observe, the stronger that evidence becomes. And so the question remains, what are chances? That's what we'll turn to next time. So first we'll link together the 3 ideas of probability that we've talked about: degrees of belief, relative frequency, and chance. And then we'll conclude our discussion by talking about what chances might actually be. So have a go at your self-reflection questions, and I'll see you all next time.